Multi-layer perceptrons, or MLPs, are the workhorses of modern machine learning. They excel at finding hidden patterns within data, which makes them incredibly versatile for tasks like image recognition, natural language processing, and even financial forecasting. Imagine trying to teach a computer to recognize a cat in a picture. To us, it's instinctive, but a computer sees only pixels. MLPs bridge this gap. They learn complex relationships between those pixels, identifying features like edges, shapes, and eventually the entire cat. This ability to decipher patterns makes MLPs invaluable. They power recommendation systems, translate languages, and even diagnose diseases from medical images. Their applications are incredibly diverse. The key to their power lies in their structure. MLPs consist of interconnected layers of neurons, simple mathematical units. These neurons work together, passing information through the network and gradually refining their understanding of the data. In this essay, we'll embark on a practical journey into the world of MLPs. Our mission: build an image recognition system to classify handwritten digits. Think of it as creating a mini version of the technology that helps digitize handwritten forms or sort mail. We'll be using the MNIST dataset, a classic in machine learning. It contains thousands of images of handwritten digits from 0 to 9. Our MLP will learn from this data, identifying the key features that distinguish a 3 from an 8 or a 7 from a 1. This task, while seemingly simple, encapsulates the core principles of MLP-based image recognition. We'll see how the network learns from raw pixel data to make accurate predictions. Our goal is to not just build a working model, but to understand the why behind every step. We'll delve into the code, exploring the layers, activation functions, and training process that bring our MLP to life. Let's peek under the hood and see how our MLP is structured. Imagine it as a network of interconnected layers, each with a specific role in processing information. This is where our image data enters the network. Each pixel in the image is represented as a separate input neuron. We'll use 2 hidden layers, each containing a number of neurons. The output layer has 10 neurons, one for each digit from 0 to 9. Import TensorFlow as tf_model =tf.keras.models.sequential. tf.keras.layers.dense 128 activation ReLU hash hidden layer 1 tf.keras.layers.dense 10 activation is softmax hash output layer. We'll be using the ReLU activation function in our hidden layers. The output layer uses the softmax function, providing probabilities for each digit. Now that our MLP is built, it's time to train it. This is where we feed it data and it learns to recognize patterns. We split the MNIST dataset into 2 parts, training and testing. The MLP learns from the training data, adjusting its internal parameters, weights and biases to minimize errors. The testing data is used later to evaluate how well the trained MLP generalizes to unseen examples. Training happens in cycles called epochs. In each epoch, the entire training dataset is fed to the MLP. The network makes predictions, calculates the error, loss, and adjusts its parameters to reduce this error. These measure how off the MLP's predictions are from the actual labels. We'll be using the categorical cross-entropy loss function, which is well suited for multi-class classification tasks like ours. Model.compile_optimizer Adam loss =, sparse _categorical _cross-entropy metric/accuracy. Model.fit x_train y_train epochs =, 5. During training, we aim to minimize this loss function. We use an optimizer like Adam in our code to adjust the MLP's parameters iteratively, gradually improving its accuracy with each epoch. Section 5. Overcoming the hurdles. My MLP journey. Building and training an MLP isn't always smooth sailing. Here are a couple of challenges I encountered and how I addressed them. Overfitting. This occurs when the MLP becomes too specialized to the training data, performing poorly on unseen data. I mitigated this by implementing dropout regularization. Dropout randomly turns off some neurons during training, preventing the network from relying too heavily on any single neuron and improving its ability to generalize. Choosing hyperparameters. Hyperparameters are like the knobs and dials of our MLP. Things like the number of hidden layers, neurons per layer, and learning rate. Finding the optimal values requires experimentation. I use techniques like grid search and cross-validation to systematically explore different hyperparameter combinations and identify the best performing setup. These challenges highlight the iterative nature of machine learning. It often involves experimentation, fine-tuning, and a bit of trial and error to achieve the desired results. Section 6. From data to insights, running our image recognition model. Let's walk through the steps of loading our data, training the model, and finally testing its performance. 1. Data loading. We start by loading the MNIST dataset using TensorFlow's built-in functionality. The data is already split into training and testing sets, making our lives easier. 2. Data pre-processing. We normalize the pixel values to be between 0 and 1. This helps with training stability and convergence. 3. Model training. We use the method to train our MLP on the training data for a specified number of epochs. 4. Model evaluation. Finally, we use the trained model to make predictions on the test data and evaluate its performance using metrics like accuracy. This step-by-step process takes us from raw data to a trained MLP model ready to classify handwritten digits. Section 7. Results that speak, visualizing success and benchmark comparisons. Our trained MLP achieves an impressive accuracy of over 97% on the MNIST test set. This means it correctly classifies over 97 out of every 100 handwritten digits it has never seen before. We can visualize the results using a confusion matrix. This matrix shows us which digits the model is confusing, providing insights into its strengths and weaknesses. Comparing our results with benchmarks, we see that our MLP performs on par with other state-of-the-art approaches for MNIST digit recognition. This demonstrates the effectiveness of MLPs for this type of image classification task. Section 8. MLPs in the wild real-world applications and future trends. The applications of MLPs extend far beyond recognizing handwritten digits. They power a wide range of real-world technologies, including image recognition. From self-driving cars to medical imaging, MLPs are used to identify objects, faces, and even anomalies in images. Natural language processing. MLPs are used in machine translation, sentiment analysis, and chatbots, enabling computers to understand and generate human language. Financial forecasting. MLPs can analyze market trends and predict stock prices, assisting investors in making informed decisions. The future of MLPs is bright. Researchers are constantly working on improving their efficiency, scalability, and ability to handle even more complex tasks. New architectures, training techniques, and applications are constantly emerging, pushing the boundaries of what's possible with these powerful neural networks. Section 9. A tale of two networks, Siamese networks for duplicate detection. Imagine you're building a system to identify duplicate questions on a forum. This is where Siamese networks shine. They're particularly good at measuring similarity between inputs. Unlike traditional MLPs that learn to classify individual inputs, Siamese networks consist of two identical subnetworks. These subnetworks process two different inputs simultaneously, but importantly, they share the same weights. Instead of directly classifying the inputs, Siamese networks focus on learning a similarity function. They output a measure of how similar or different the two inputs are. This makes them ideal for tasks like duplicate detection, identifying duplicate questions, images, or documents, face recognition, verifying if two images belong to the same person, signature verification, comparing a signature against a known sample. In essence, Siamese networks provide a powerful way to leverage the pattern recognition capabilities of MLPs for tasks that involve comparing and contrasting inputs. Section 10. Siamese network implementation, code and evaluation. Let's outline how we'd implement a Siamese network for our question duplicate detection task. First, data preparation. We'd need a data set of question pairs labeled as either duplicates or not. Next, Siamese network architecture. We'd create two identical subnetworks, each taking a question as input and outputting a feature vector. Then, distance function. We'd use a distance function like Euclidean distance to calculate the similarity between the feature vectors produced by the two subnetworks. After that, training. We train the network using contrastive loss functions. These functions encourage the network to minimize the distance between feature vectors of similar question pairs and maximize the distance for dissimilar pairs. Hypothetical code snippet. Define the subnetwork architecture. Input A and B using TensorFlow Keras layers. Use the same subnetwork for both inputs. Encode A and B using the subnetwork. Compute the distance between the encodings. Define the Siamese network using TensorFlow Keras models. Compile and train the network. Finally, evaluation. We'd evaluate the network's performance using metrics like accuracy, precision, and recall on a separate test set of question pairs. By carefully designing and training a Siamese network, we can effectively leverage the power of MLPs for the challenging task of identifying duplicate questions.